The first elimination mechanism we're going to cover is called the E2 mechanism, or the uh, elimination bimolecular mechanism. It occurs by a base removing a hydrogen on the carbon that is attached to a carbon which has a leaving group. So this base will remove this hydrogen. That would lead to the electrons in this bond forming a double bond here. And then that would lead to the elimination of the halogen. That goes through a transition state, which has a partial bond between the base and this hydrogen. It has a partial bond broken here, partial double bond forming, and partial bond broken between the carbon and the leaving group. After both the halogen and the hydrogen are eliminated, we end up with an alkene product. Overall, notice this is a single mechanism step. It looks like two because we're going through a transition state like all mechanisms have, but in reality, it's just a single mechanism. So this should remind you a little bit of the SN2 reaction in terms of mechanism steps. There, we also had a single mechanism step. The E2 reaction has a rate equation that is second order overall. The equation can be expressed as rate is equal to the constant times the concentration of the alkyl halide, which is raised to the 1 power, and we multiply that times the concentration of the base, which is also raised to the 1 power. If we add up the two exponents in this equation, we get a second order overall equation. This is very similar to the SN2 reaction, which is also second order overall. The E2 reaction is also stereoselective. It is stereoselective because the stereochemistry of the reactant will predict the stereochemistry of the product. So stereoselective reactions in general means that the uh, product is predictable in terms of stereochemistry. For the case of the E2 reaction, we predict it based on the stereochemistry of the reactant. So E2 reactions will always undergo through an anti-periplanar geometry. So we'll discuss this in detail in a moment, but basically the anti-periplanar geometry refers to having the hydrogen that is going to be eliminating the carbons that are part of the reaction and the leaving group that is attached to the other carbon, uh, all being on the same plane. So if we drew a plane through this molecule, it would cut through O4, and the hydrogen is also on the opposite side of the tosylate group. That is what makes it an anti-periplanar geometry. So once you have that geometry for the E2 reaction, you can easily predict the product. So a base would remove this hydrogen. That would lead to forming a double bond there, and by eliminating the tosylate group. And so notice the phenyl group is facing away, so is this hydrogen. So those two groups would be on the same side of the alkene. This methyl group is forward, so is this methyl group, so they're both on the same side of the alkene product. So overall, we obtain the E stereochemistry for the double bond from this particular stereoisomer. Underneath, we have another stereoisomer that differs from the first one in that the methyl group is on the opposite side um, from the previous stereoisomer. So it is back here, it is forward here. The hydrogen switch places too, so this one is facing back and is facing forward here. So we have essentially swapped the hydrogen and the methyl group. The stereochemistry of this carbon atom is identical in both stereoisomers. So for that reason, these two stereoisomers are really diastereomers or epimers, if you want to be more precise. So we're changing the stereochemistry of one stereocenter not the other, so they are diastereomers or epimers of each other. In the second stereoisomer, once we have the anti-periplanar geometry between the hydrogen and this tosylate group, the base can remove this hydrogen, and then a double bond would form here. And so that would mean that this phenyl group, which is facing backwards, and this methyl group, which is facing backwards, would be on the same side of the molecule, while this methyl group, which is forward, is on the same side as this hydrogen as shown here. So overall, we obtain this Z stereochemistry in this particular stereoisomer. Periplanar geometry simply means that all four reactant atoms in the reactants are in the same plane of the molecule. So in the case of an E2 reaction, the reactant would be an alkyl halide that has a carbon attached to a hydrogen. The hydrogen we're eliminating. And then we have a carbon here next to that first carbon that has a leaving group, some X group. It could be a halogen or a tosylate group. All four of these reactant atoms are all in the same plane. So if we drew a plane right here, it would cut through all four atoms. There is an orbital reason of why this particular geometry is required for the elimination reaction, the E2 reaction. The explanation is that the sp3 orbital of this carbon that is used to make a bond to the hydrogen and the sp3 orbital of this carbon, so the big lobe here and the smaller lobe is all part of the sp3 orbital of that carbon that is used to make a bond to this leaving group. That sp3 orbital and this sp3 orbital are lined up when we have a periplanar geometry that once we eliminate the hydrogen and the leaving group, they can easily switch from or rehybridize from being sp3 in this reactant to being p orbitals that make up the double bond of the alkene product that we obtain. There are two types of periplanar geometry, syn and anti. Let's discuss syn first. So syn periplanar refers to having the hydrogen, which we're going to eliminate, and the leaving group that we're also eliminating in forming the product being on the same side of the molecule. So you can see that here, these are on the top side. You can clearly see that the hydrogen and the X group are on the same side of this particular geometry. So that's referred to as syn periplanar. Now, why is this not favored in the E2 reaction? Well, the reason is that it leads to eclipse bonds. So this bond here is being, or is eclipsing this bond. These bonds here are also eclipsed. These two here on the left are also eclipsing each other. So it is a geometry that, although is periplanar, it is an unstable geometry because of those eclipsing interactions. So syn periplanar is not ideal for the E2. The favored or the required geometry for a E2 reaction is the anti-periplanar geometry. That is when the hydrogen and the leaving group that we're eliminating are on opposite sides of the molecule. They are periplanar, so meaning in the same plane, but they're on opposite sides of the molecule. So this is referred to as anti-periplanar geometry. If we look at the Newman projection, we could clearly see that the hydrogen and the X group are on opposite sides of the Newman projection. We also have stagger bonds. So for example, this bond to the leaving group is splitting these two bonds on the front carbon, and every other bond from the front carbon is staggered compared to the bonds in the back carbon. So this is a very low energy conformation, and this is the reason why we use this particular conformation as opposed to the syn periplanar geometry in the E2 reaction. In this question, we want to predict the product that would be obtained by taking this alkyl halide and mixing it with a base such as potassium hydroxide. In order to predict the product from this reaction, we want to focus in on the carbon that has the leaving group. So the product would be formed by eliminating a hydrogen from an adjacent carbon. So for example, we could remove a hydrogen from this carbon here, or we could remove a hydrogen from this carbon here. Both of those carbons, or removing a hydrogen from both of those carbons, would lead to the same alkene product based on the symmetry of this molecule once we eliminate this halogen. So a double bond there is the same as having a double bond there. We can also remove a hydrogen from this carbon. That would lead to a double bond there once we remove the hydrogen and this halogen. So that's a second possible alkene product. And you can see those here. So this is the product that forms from removing a hydrogen from the methyl group. And this is a product that forms from removing one of these two hydrogens. So if we notice, this double bond is more substituted. So there's two alkyl groups, there's one alkyl group, and one hydrogen. So overall, three alkyl groups. This is basically a tri-substituted double bond. Here we have a double bond that has only one and two methyl groups. We have two hydrogens, so this is less substituted. This is the anti-cis product. This is the cis product. Since the base is fairly unhindered, the cis product should be the major product. This question is going to ask us to basically predict the reactant, the alkyl halide that we would use to make this particular alkene product. So we want to think about this backwards. We have a double bond here. Where do we want to put the halogen? To answer this question, we want to look at the product that we're trying to form, which has a double bond between these two carbons. So looking backwards at what we started with, the alkyl halide would have to be one that has the halogen either on this carbon or on this carbon. And we would be removing a hydrogen from the opposite carbon. So if we started with a reactant that has a halogen here, as shown in this reactant, when we add base, we would be removing a hydrogen from the adjacent carbon. So here is the carbon that has a halogen. The next carbon over has two hydrogens, so the base can remove one of those. And that's actually the only possibility in using this reactant. So this is the nice thing about using this particular reactant. There's only one possible outcome. When the base comes, it can only remove these hydrogens and nothing else. However, if we gave an answer that has the halogen being on this carbon, so in other words, thinking about this backwards, where we put the halogen here, that would put the bromine here. If we add base, there's two possible outcomes. The base can remove a hydrogen from this carbon, so it's always the carbon that is adjacent to the carbon with the leaving group. So if we had a bromine here, our base can remove a hydrogen from this carbon, but it could also remove it from here. So you can end up with a double bond here or a double bond here. The double bond here would give us the product we want, but the double bond here would not give us the product that we want. So by using an alkyl halide that has a bromine here, we create the scenario now where there's two possible products. That's not ideal. If we're trying to get a high yield of the product, we want to use a reactant that would lead to a single product. So that would be this particular alkyl halide that I already have on the slide. In this question, we want to draw a Newman projection of the reactant, which is given here, 1R, 2R, 1,2-dibromo, 1,2-diphenyl-ethane. We want to draw that in a Newman projection, keeping in mind that this is going to be an E2 reaction, which means we want to have the reactant in a anti-periplanar geometry. So to answer this question, we want to first draw our reactant with the right stereochemistry. So as you can see here, we have a carbon that has a phenyl group and a bromine group. This is already in R stereochemistry, and then this carbon has the same R stereochemistry as well. Then we want to take this particular compound and convert it into a Newman projection. So if we were looking at this molecule through this carbon to carbon bond, we would get a Newman projection. So in the front carbon, this one here, let's say, we would have a bromine to the top left and a phenyl group to the top right as we're looking at it this way. This bond here would be down. In the back carbon, which would be this one here, we would have a phenyl group to the top left. So that's why this is going this way and is wedged. And then in the back carbon, we would also have a bromine to the top right. That's this bromine. So it's wedged and meaning is up. And it is obviously in the back carbon. This hydrogen is down as indicated by this dash bond. So that bond here is this back carbon to hydrogen bond. Now we want to double check that this is in an anti-periplanar geometry. What that really means is the hydrogen that we're eliminating has to be anti to the bromine we're also eliminating. So we can, for example, we could take this hydrogen and put it anti to this bromine in the back, or we could take this hydrogen in the back and put it anti to this bromine. So we have two options. But what we can't do is put this hydrogen, which is attached to the same carbon, anti somehow to this bromine. All right, so it's always the hydrogen on an adjacent carbon to the carbon that has the bromine. So if we rotate the front carbon, so notice in going from here to here, the back carbon stays the same. So the phenyl is to the top left, bromine is to the top right, hydrogen is down like it is here. However, we have rotated the front carbon, so this bromine now goes a little bit to the right. So now it's facing up. This phenyl group goes down here, and then the hydrogen in the front here gets moved this way. So we have just essentially rotated this clockwise about. So if this is 360 degrees and we're splitting it by 3, it means that in going from here to here, sorry, it's actually it's 360, and we're dividing it by 3. And going from here to here is 120 degrees. So and going from here to the middle is 60 degrees. So if we rotate it 60 degrees, each one of these front groups, we obtain this molecule or this projection. It's actually the same molecule as we started with. Now, notice this bromine is opposite to this hydrogen, so they are anti to each other. And we can do an elimination where a base can come, remove this hydrogen, and that would lead to this bromine leaving. There will be a double bond form in between. That would lead us to this product here, where the phenyl group and this hydrogen are on the same side, and then the bromine here and the phenyl are on the same side. So this is showing a Newman projection of what's left over in the product. There's actually a double bond between these two carbons in the Newman projection. If we sort of spread that out, we would get this structure here where the hydrogen and the phenyl are on the same side. So this hydrogen and phenyl on the same side. And this phenyl group, which is that one, is on the same side as a bromine.